So this is a talk all about the nearest star to the Sun, Alpha Centauri, and let's get the ball rolling. The first thing to notice is you can't see it from Cambridge or anywhere in the northern hemisphere because it's really quite a long way into the southern sky. It's in the constellation of Centaurus, which is one of the largest constellations. I think Ursa Major in the northern hemisphere is the largest, but this is Centaurus here, and you can see we have the Southern Cross here, and the south pole of the sky is just off the bottom of the screen. But the star in question is this one here, marked with the handy purple arrow, and it's Alpha Centauri because it's the brightest star in that constellation of Centaurus. It was spotted that it was a binary star, in fact, a long time ago in 1689, so not long after the invention of the telescope. I think that was 1610, wasn't it, with Galileo? So telescopes had moved on a little bit since then, but nevertheless, it was recognized that when you looked at it with a telescope, you could see what appeared to be a single star as two. And I love this photograph. This was one that somebody took in broad daylight, which is why the sky is blue. So you can see Alpha Centauri and its companion in broad daylight.
Amazing.
So here's, again, this is the star we're talking about, this one here, looking yellow. There's the Southern Cross. And what first drew people's attention to it was that they were mapping the sky and looking to measure what's called the proper motion of stars. That is the movement against the distant background of apparently stationary stars that are a very, very long way away. So, in fact, an astronomer called Henderson was on the island of St. Helena down in the South Atlantic, of measuring the proper motion of stars in the southern sky for the first time. He must have had fantastic seeing conditions down there with no light whatsoever, because St. Helena really is a very remote place. I think it's where Napoleon was eventually sent on exile, wasn't it? And what shocked him was he measured the proper motion of Alpha Centauri, and it was moving across the sky quite fast. Now that either means it is moving very fast or it's quite nearby. So he measured the parallax, the amount that the position appears to change due to the motion of the Earth around the Sun. Effectively, you can use the Earth's orbit diameter of 300 million kilometers as a baseline and get a very, very long, thin triangle out to the star and measure the angle at the tip of that thin triangle. And from that, you can work out the distance. And he did that and was so surprised that he took several years before he published the result. In fact, it was 1839 before he published the distance, saying it's 4 light years. He couldn't believe that he'd found a star that was that close. All the others that had been measured up to that point were much further away. And as it says on the slide, we now confirm that that's very good measurement, modern figure 4.37, making it the closest star to the Sun, which is why everybody's always heard about it. But as we said, it's a binary star system. A and B are the two components. They orbit round their common center of mass. And this diagram is a little bit complicated, but trying to show that. And it's showing it from the perspective of Alpha Centauri A, the larger of the two, being held still. And the position of B is then marked here. So it's orbiting down this way, and probably, what is it, about here by now, 2021. And the orbit is elliptical, but it's not as elliptical as that diagram makes it look, because we're looking at it almost edge on. If you stretch the ellipse out to look at it from the perpendicular direction to the plane of the ellipse, then you would see it as the shape that's shown around the outside. That's not really a third star. They're just in this diagram showing you what the shape of the orbit would look like if it wasn't for the perspective.
Mm-hmm.
Now, when we look at it, the angle between the A and B stars varies as that ellipse is shown in different positions, and the maximum separation that you can see is just 22 arc seconds, which is an easy separate for an amateur telescope. That happened in 1976 and is going to happen again in 2056. As with all things, we in the present are just about at the closest. They were 4 arc seconds apart in 2016, and that's beyond the capabilities of the smallest amateur telescopes. Larger ones will be able to separate two things that are 4 arc seconds apart if you get a clear night with good stable seeing. So at the moment it's quite a challenge. So 4 arc seconds in 2016, it's opening up. It was about 5 now. So you can see as of 2019, 4.92. So it's getting better and easier to actually see them. But that's no use for my telescope because the Earth's in the way. As we said, you'd have to go to the southern hemisphere, and of course you need a reasonably large telescope, so a portable one's no good. But in fact, the system is a triple star system, and element C, which we now call Proxima Century, was discovered quite a long time later. So the original double was discovered in 1689. It wasn't until 1915 that Robert Innes managed to spot that there was another star that shared the same proper motion across the sky, and when he measured the parallax for it, he spotted that it was the same distance, and reasoned that therefore it was part of the Alpha Centauri system. In fact, it's slightly closer to us than its brethren. It's 4.24 light years, but that's just because at the moment it's orbiting around the common center of mass is on our side of the system. And you can see in the little animation there, that is Proxima Century moving against the background stars in 5-year steps, showing really quite a large amount of proper motion from year to year. Easy to measure. So again, this is where Alpha Centauri is, and Alpha Centauri A and B both appear together there. Proxima Centauri is actually clearly separated from them. Here again we've got the stars of the Southern Cross, and this one here, this is Beta Centauri, not to be confused with Alpha Centauri B. So if we look at that with a little bit of zoom in, Alpha Centauri A, there's the 4 arc seconds between A and B, but Proxima Centauri is over here, mixed in amongst the star clouds of the Milky Way, which is why it took so long before it was spotted. It's actually clearly, degrees away from Alpha Centauri. So it took a while before it was identified. Now we said that this little group then of Alpha Centauri A, B and Proxima are the nearest stars to the Sun. Here's the Sun. We talked about the Oort cloud last week, I think. Out here, 4 light years and a little bit, we get to Alpha Centauri. The next nearest star is over here, Barnard's star. That has again a high proper motion, the highest of all in fact, and was measured and the distance gained by parallax in 1916, so round about the same time that Proxima was identified. Barnard's star was discovered and came out at 6 point something light years, 6.2 light years I think. These other guys out here, much more recent discoveries with these exciting names. This is the Wide Field Infrared Survey using the WISE telescope, and these are brown dwarfs out here just beyond the 6 light year mark as the next nearest objects to the Sun. And those are failed stars. They're intermediate size objects between a giant planet and a star, a bit bigger than Jupiter. I think if Jupiter would have to be 75 times more massive to become a star, and these things are probably 10 times to 20 times the mass of Jupiter. So that's where things are now, but we can also plot the future and indeed back calculate into the past the path of some of these nearby stars relative to the sun. So the dotted blue line here, that's now, and Proxima Centauri, this orangey yellow line here, is the nearest now, followed by Alpha Centauri, followed by Barnard's star, and then ignoring the brown dwarfs, we go out to the next proper star, which is this one, Leyland 21185, and then Ross 248. But you can see that the distance is changing. Alpha and Proxima are swinging towards us and getting closer, and they will do so for some considerable time to come, about 25,000 years, I think, and then they'll start to separate away from us again. Likewise, Barnard's star is approaching us, but it's not quite going to take the record from Alpha Centauri system. It's going to get close to the same distance, but then turn away from us again due to its different path. The ones that are going to become the nearest star to the sun in the future are the red dwarf star Ross 248, which in this time here, so about 30 or 40,000 years into the future, that will be the nearest star. And then a little bit later, once it's retreated, another red dwarf, Gliese 445, will hold the record briefly, but then it'll be back to Alpha again for quite some time. So we know that there are 3 stars, and that we can see 2 of them as a single entry, and the third one widely separated enough to be identifiable as a clear separate star. But what are the stars actually like? Well, the 2 main ones are very similar to the sun. Alpha Centauri A, officially called Rigel Kentaurus, which translates as the foot of the centaur, and Alpha Centauri B, Tollyman, the ostriches, which was an Aborigine name for the constellation of the Centaurus. And so when they were looking for a name to give to Alpha Centauri B, they used Tollyman. And these 2 orbit each other in 80 years, as we've seen, with an elliptical orbit from 35 astronomical units, which is just bigger than the distance from the Sun to Neptune, to a close approach of 11 astronomical units, which is around about the orbit of Saturn. So there's quite a big gap inside where neither of them would go, but they're filling really what we would consider to be the outer solar system, that Alpha Centauri B is traversing the whole of the outer solar system as it makes its repeated orbits round. And then Proxima Centauri, Alpha Centauri C, is much smaller. It's a little red dwarf compared to these 2, which are fairly similar to the sun. And it's slightly closer. It's actually 13,000 astronomical units closer, or 0.2 of a light year. So Alpha Centauri A is a little bit hotter and a little bit more massive than the sun, 110% the mass, gives out 152% of the light, and has a temperature that's just a little bit warmer. The sun is 5722 Kelvin, and Alpha Centauri A 5790 Kelvin, so about 70 degrees hotter. Still gets classified in the same G2 class of yellow dwarfs. Spins on its axis in 22 days. That's a little bit faster than the sun, which takes 26, and that's typical of the larger the star, the faster they tend to spin. It's to do with mass and angular momentum, a bit like a skier, it's not a skier, a skater pulling their arms in and going into a spin. If the more mass you pull in, the faster you will end up spinning. So if the skater was holding a massive dumbbell in each hand and went into a spin and then pulled them in, they would spin up even more. And so the larger the mass, the faster they tend to rotate. It shows magnetic activity, and we've even been able to detect star spots on the surface. Although the activity's died down since 2005, and it's a bit like the sun went into what was called the Maunder minimum a couple of hundred years ago, where there were no sunspots for a long period of time. So maybe that's a characteristic of these sun-like stars. Alpha Centauri B, a little bit smaller. It gets classified as a K-type star, more orange than yellow. Only 90% of the mass, so not that much lighter, but it makes a huge difference. The luminosity, the amount of light, is just under half that of the sun, as opposed to 150% for Alpha Centauri A. And the temperature's down by around about 500 degrees. You can see that there. Rotates more slowly because it's smaller, 36 days. So that fits that same rule. More magnetically active, which also goes with the smaller stars. They tend to be more active. And this is to do with the way that their internals get convected. And it has a sunspot cycle. We have a sunspot cycle of 11 years usually, and Alpha Centauri B has an 8.2 year sunspot cycle, and sometimes has flares. We've detected at least one, and strong X-ray emissions from it. And then we have C, Proxima, an M-type red dwarf, much cooler, just over 3,000 degrees, 12% the mass of the sun, and only 1/20,000th of the light output. No wonder it's so faint and hard to see. Rotates in 83 days, so smaller and more slowly rotating, produces more flares, and that's characteristic of the smaller stars, and again strong X-rays coming from those flares. But 12% of the mass of the sun is almost as small as a proper star can be. The absolute lower limit for proper nuclear fusion to occur, converting hydrogen to helium, is 7.5% the mass of the sun. So Alpha Centauri C, Proxima, is only just managing to be a red dwarf star. If it was much lighter, it would have been one of those brown dwarfs, a failed star. Now, for a long time, there was a controversy about its orbit. Until 2017, it wasn't known whether Proxima was merely passing by Alpha Centauri or whether it was in a bound orbit, gravitationally bound to the AB pair. But the Gaia satellite that's out there measuring the 3D structure of the Milky Way and pinning down the position and movement of 1 billion stars has tracked down and measured Proxima's movement sufficiently accurately that we can now say for sure that it is in a captured orbit, although it's a very long one. It takes just over 500,000 years, as you can see on the slide there, to go round. And slightly elliptical, goes from 4,300 AU to 13,000 AU. So again, our bad luck was to find it at the point where it was moving the most slowly, because that's what happens when you're at the extreme outer point of your orbit, which is where it is at the moment, the apastron point, the distance furthest away from this parent star. That makes it move more slowly by Kepler's laws. So how old are these stars? Are they relatives of the sun? They're nearby and sun-like. Could they be the sun's sisters that were all born in the same original star cluster? Well, it's a little bit difficult to estimate the ages, and the figures come out with a range from 4.85 billion years to 6.52 billion years. So that's perhaps arguably just a little bit older than the sun, because we think the sun is between 4.5 billion and 5 billion. But it's not beyond the bounds of possibility that these ranges overlap. If it turns out that the Alpha Centauri stars are at the younger end of things, then that 4.85 might match the value for the sun. So we're still looking into that one. So what's going to happen in the future with them? Well, star A, being 110% the mass of our sun, will have a shorter lifespan than our sun, because it's burning faster due to the heavier mass. And even though it's got more fuel due to the heavier mass, it burns disproportionately more quickly. I think the rate of fusion goes up something like the fourth power of the mass, which is why it's so much brighter. Just because it's 10% heavier, it's 50% brighter. And that shortens the life. So the sun will live 10 billion years and is 5 billion years old. Alpha Centauri A is about 5 billion years old, but it's only going to live 6.8 billion before it runs out of fuel. So in roughly 2 billion years time, it's going to take the next step on its life cycle and turn into a red giant, and then a planetary nebula, shedding its outer layers, and then shrink down to a small white dwarf, about half a solar mass left in the white dwarf there. B, of course, being slightly lighter than the sun, 90% of the sun's mass, and only 50% of the output, is going to live twice as long as the sun, 20 billion years. And so it also being 5 billion years old means that it's still a teenager, and it's got another 3/4 of its life to go, all the way out 15 billion years. But it will undergo a very similar process of going red giant, planetary nebula, white dwarf, probably slightly smaller white dwarf. Well, that age and lifetime is nothing. Proxima C is going 12% of the mass of the sun and a 20,000th of the solar output. That's got an expected lifespan of 2 trillion years, way longer than the age of the universe so far. And in fact, no red dwarf star, however far back in time it was born, has got anywhere near running out of fuel yet. They're only still really in nappies. And it will eventually, we think, just form a helium white dwarf. But we don't know because we've never seen one, because we will have to wait about 1 trillion years before the first red dwarf stars begin to go through that process, which is a ridiculous length of time. Now, with A and B being so close together, A is going to turn into a white dwarf first due to its shorter life, but in 15 billion years time, when B also turns into a red giant in that life cycle, it will swell up, and as it does so, it loses the gravitational hold on its outer layers, and so material will begin to be lost from the much expanded red giant B and will spiral over onto and be gravitationally pulled down onto the surface of the white dwarf, formerly known as A. And sometimes that can cause catastrophe because it can lead to a type 1a supernova. But I don't think it will in this case, because for that to happen, the mass limit of 1.44 solar masses has to be exceeded, the Chandrasekhar limit, the upper mass limit for a white dwarf. Any more than that, put another teaspoonful of mass on and they explode violently as a type 1a supernova. But we will have here probably a half solar mass white dwarf, and then the entire mass of Alpha Centauri B is only another 9/10. So if you add those two together, if they completely merged, you still don't quite have enough mass for it to detonate. So we'll end up with a pair of white dwarfs, roughly half a solar mass each, orbiting each other, and then they will gradually spiral inwards over trillions of years and eventually collide. And when they do, that can lead to a very similar supernova explosion like a type 1a. So eventually that will happen. But what about planets around these stars, I hear you ask? Well, we already know of 2, and this is brand new news really in astronomical terms. Proxima Centauri, the little red dwarf, has 2 planets. It has at least 2 planets, I should say. It's got Proxima B. Now we give stars in multiple systems uppercase letters, going uppercase A, B, C, and so on, and we give the planets lowercase letters, but for some reason we start at B. We never start at A. So it's very confusing. So the first one to be discovered was Proxima B. And this is an Earth-sized planet, just a little bit larger than the Earth, a little bit more massive, orbiting around Proxima at only 0.05 astronomical units and whizzing round every 11.2 days. That was discovered 4 years ago in November 2016. And Proxima C, the second planet, was discovered in 2019, just last year. I think it was June they discovered it, and they announced it a few months later once they'd got their paper published. And that is in a 1.5 astronomical unit orbit around, which takes 5.2 years to travel around. And there's a hint now of a third object in a even smaller orbit than Proxima B. So this, if it's confirmed, will be Proxima D in a 5.15 day orbit, right in close. And it's a little tiny planet if it's there, just 0.29 of the Earth's mass, so similar in mass to Mercury, and actually placed in a fairly similar and rather toasty position, up close to the surface of the star almost. So Proxima B, found in 2016, and that was discovered using the radial velocity Doppler shift method. They looked for the redding and bluing color changes of the spectrum of the light from the star Proxima, and observed that that was wobbling backwards and forwards as shown in this little plot down here. And you can see that there is an 11-day period in that, which was caused by the gravitational tug from Proxima B. And from that, we can work out that the mass of Proxima B must be at least that minimum figure there, 1.173 Earth masses, fairly precise. But it could be up to 2.8. And the reason we have the uncertainty is we don't know if the plane of the orbit is nearly in our line of sight, in which case we would get the maximum amount of wobble of the star per unit mass of the planet. Or if the orbit of the planet is tipped over compared to our line of sight, then the movement to and fro of the star towards the planet won't be quite aligned with our line of sight and will be reduced. And so we will underestimate the mass if we don't take account of that. So if it were almost at right angles, then we would be estimating nearly 2.8 Earth masses. Now, with Proxima being a cool red dwarf with a 3,000 degree surface temperature of the star, being only 0.05 AU away is quite a reasonable position to be in. This slide doesn't read quite right. It says the temperature should be around minus 39 degrees, but unfortunately the minus has stayed on the line above there. Sorry about that. But that's trying to say minus 39 degrees. So warm compared to the sometimes really freezing temperatures that we see that are enough to freeze nitrogen and so on some of the moons of Saturn, for example, but not warm enough for liquid water, unless it's got a thick atmosphere. And that's very interesting, because if it had a thick atmosphere, it would warm it up by the greenhouse effect and could bring it to a habitable temperature. It would have to have quite a substantial atmosphere. The Earth's atmosphere warms the Earth from minus 15 that it would otherwise be to about 20 degrees centigrade. So a 35 degree uplift is what we're getting at the moment. And we're worried about it going any higher. So here we're looking for about a 50 degree uplift in the temperature, maybe a 40 degree uplift in the temperature. So you need a bit of a thicker atmosphere. But the planet has a greater mass, and if perhaps it was at 1.5 to 2 Earth masses, it would probably be able to hold on to a very decent sized atmosphere. Now, the unfortunate thing from a habitable point of view as well is that being close to the star has a disadvantage, that you also receive a lot of very strong radiation in the form of the stellar wind, and also a lot of X-rays from any flares that occur on the star. And unprotected, that would be very bad. But again, if it's massive enough to have a very thick atmosphere, then that could provide enough protection for the surface to be a habitable zone. And so that's a very, very interesting situation. Just to give you a sense of the scale, here's the Sun and Proxima Centauri size for size. The Sun is way larger. And here is Proxima B and the Earth size for size. And again, we've got Jupiter and Saturn. So you can see that actually Proxima is only marginally larger in diameter than a giant planet, just over that threshold that makes it a proper star. Now, another problem that has been discussed as regards whether Proxima B might be a candidate for life is that these red dwarf stars misbehave for a couple of 100 million years after they're formed. They're very, very turbulent and active during that first period of their existence. And that tends to increase the heat output, which would move the habitable zone further away, leaving Proxima B a bit too warm and a bit too toasty for comfort. And so that might have then stripped away quite a lot of atmosphere. And then as the star cools down to where it is today, the habitable zone moves inwards. So the question is, did any water and atmosphere survive on Proxima B? But I think you've got to remember that actually the Earth wasn't habitable for the first 500 million years or so of its existence. It was probably a molten ball of lava with the leftover heat of its formation. And so Proxima B would probably be that as well. And as with the Earth, water might well have been delivered later, after the surface had cooled down and after the star had settled down. And that might well have been able to solve the problem of habitability. The stellar wind might blow the atmosphere away is another problem. And a lot therefore depends on whether it has a magnetic field, and that depends on whether it spins enough to create a magnetic field. If it does, if it's spinning reasonably fast, then it should be protected in the same way that we are. But a large enough planet, if it was maybe 2.5 Earth masses, would probably have a super thick atmosphere, and that in itself might be enough to render it habitable. So there's a lot we still need to understand about this before we can really have any confidence in our predictions of livability. What about Proxima C then? This is an artist's impression of Proxima B and the larger Proxima C. So discovered just in 2020 and announced, and it is a larger planet, 7 Earth masses. That's much larger than the Earth, obviously, and smaller than the outer giants Uranus and Neptune. I think Neptune is about 16 Earth masses. So it's an intermediate sized planet, a super Earth or a mini Neptune, depending on your point of view and depending on what it's made of. Takes 5.2 years to go around in its orbit. And at that distance from the star, it's chilly, minus 234 degrees centigrade. So we're looking more at a mini Neptune, perhaps, in terms of temperature. Now, amazingly, we have directly imaged Proxima C. We have a direct telescope image of it. We've not managed to do that with Proxima B. It's so close to the star and very small that that's a real challenge. But here is the discovery image, if you like, Proxima itself is over there. These two blobs are distant background stars. There's a certain amount of digital noise, but this thing here, this is moving and is the planet Proxima C. Now, when they did that, it was a little bit of a surprise, because for a 7 Earth mass planet like Neptune, perhaps, at that distance from a dim star, you can work out how bright you'd expect it to be. But the brightness here was much too great. And the reason that they think it's reflecting more light is because it's got a very large system of rings that make Saturn's rings look pathetic. And so even though the mass is relatively small compared to something like Saturn, it's got this very large and reflective spread out system of rings. So again, fascinating to learn more about our nearest neighbor solar system. And I say there is a potential third planet there that we really don't know very much about. Now, just thinking about the possibility then of further planets in the system, what about planets that orbit around the A and the B stars? Is that possible? And being as they're sun-like stars, it seems like a very attractive idea that they would have formed with a similar set of planets, all other things being equal, to those that we have. But being a binary pair, that does rather mess things up. It restricts the possibilities for the orbits, because Alpha Centauri B is sweeping in and out across that outer solar system range. Now, we've had a good look and found no gas giants and no other brown dwarf failed star members of the system. So we're pretty sure there are no large objects there. Instruments are not yet perhaps sensitive enough to detect small Earth-like planets. There was an announcement in 2012 of an Earth-like planet being discovered orbiting around Alpha Centauri B, which therefore goes with the name Alpha Centauri BB, one capital B and one lowercase b. But it's been unfortunately debunked in 2015. New analysis carried out in Oxford showed that the numerical methods that they were using to analyze the data was actually generating artifacts that looked like this planet. So sorry, that was another of the planets that never were. But in 2013, a possible transit was observed where the planet passes in front of the star and blocks the light. And if that's confirmed, then it's a planet slightly smaller than the Earth, 92%, so about the size of Venus, and in a 12-day orbit around Alpha Centauri B. That's going to be pretty hot, because Alpha Centauri B is half the power output of the Sun, and being in an orbit only 12 days, you'll be much closer in than Mercury is to the Sun. So the interesting thing is you can do various simulations and calculations to try to figure out where you could have stable orbits. And you can have stable orbits well away from both stars, much as Proxima Centauri orbits the two of them and really observes them gravitationally to be a single entity. It thinks there's a two solar mass star that it's orbiting. They're so close together from its point of view. So there are orbits well outside. There are also orbits in close to Alpha Centauri A, anywhere in this sort of range is possible. And the same is true for Alpha Centauri B. You can have stable orbits in there. And these are the habitable zones from 0.5 to 1.4 AU around Alpha Centauri B, closer in than our habitable zone. And again, quite a wide range they've given there, allowing for a very large planet with a thick atmosphere at the outer edge, or a smaller planet with a thin atmosphere at the inner edge of the habitable zone. And the Earth-like habitable zone is the dotted line. Here it is for Alpha Centauri A, so out here at just over 1.2 AU, I think it is. And again, they've given a rather generous width to the habitable zones. But the stable orbits, again, you can do that calculation and show that with them at closest approach of 11 AU, you would be all right as long as you're within about 2 AU of Alpha Centauri B and a little bit further for Alpha Centauri A. So the habitable zones are places you could orbit without your orbit being badly affected by the other companion. So that's quite interesting. But you couldn't really have any giant planet companions orbiting further out because they would be disrupted by close approaches to the other star, whichever you're talking about. So the question is, do they? Well, what we have observed is that both stars show disks of dust, and this is observed in the infrared. We see excess infrared emissions around both the A and the B stars, and this is a bit like we have the dust that causes the zodiacal light in our solar system. It's the leftover building blocks of planets in our solar system, but Alpha Centauri A and B have 100 times as much, or 10 to 100 times as much mass in these dust disks. That could be because they weren't able to form any planets further out, and any giant planets would have been either collided with the other star or kicked out or thrown further into the inner part of their solar systems. So it could be that there are quite thick sort of clouds of dust, and maybe this is even an asteroid belt type structure. We don't know. It's around about 2.8 astronomical units for A and 2 AU for B. So it's just on the outer edge of the habitable zones and just on the outer edge of the stable orbit zones. So any actual stable orbits for planets would be further in. There's even a dust disk around Proxima, again showing that same sort of structure that we have in the solar system here, only at this time it's outside the orbits of the known planets, and it's more like a Kuiper belt, the leftovers that where Pluto orbits out beyond Neptune in our solar system are called the Kuiper belt. Of course, our system is proportionately larger with a more massive star, and so that's out at 35 astronomical units or so. In Proxima's case, the whole thing's scaled down due to its lesser gravity and smaller mass, and so it's the 2 to 4 astronomical unit region here where this dust disk exists. But it's indicative that there might be a full-on solar system in miniature with all the features that we have in ours. But just another way of looking at this is to look at the Sun and Alpha Centauri system as whether we should consider them to be interacting with each other. And we can look at the sphere of influence of gravity of the Sun. Anything within this zone here around the Sun out to just below 1 light year is captured by the Sun. Anything inside this larger grey sphere here is captured by the Alpha Centauri system, including Proxima. And the reason is you can do the maths. There's a little formula for this, and if you plug in 1 solar mass and you do the numbers, you get 0.76 of a light year for the Sun, but the Alpha Centauri system is just over 2 solar masses, so you plug the numbers in and you get a number about double, 1.5, 1.6 light years for the gravitational dominance zone around these things. So these are the regions in which the outer planets might orbit right around the whole lot. Anything right out towards the edge is only going to be fairly loosely attached and run the risk of being torn away as the distance between the stars changes. Though you've got to bear that in mind, and they are getting closer, as we saw. So if you were standing stargazing on Proxima Centauri B, that Earth-like planet, well, you wonder what the sky would look like. And the answer is it would look almost exactly the same as it does from Earth, because you've only moved 4 light years away. And so the distance and angles and the parallax of most of the other stars would hardly have changed. Obviously, there'd be a bright star missing from the constellation of Centaurus, because Alpha Centauri will be missing from Centaurus, and actually will seem to move across the sky tremendously fast. And you'll even be able to see the 2 separate stars of that as small disks in the distance that are orbiting around each other. So it might be quite a spectacular sight to see that. And of course, they'd be very, very bright indeed at that distance. So it might be that there is no real darkness on Proxima B, unless all 3 of the stars happen to be on the other side of the planet from you, which could make the day and night cycle quite complicated. But the sun would be a very bright star over here in the constellation of Cassiopeia, on the opposite side of the sky to where we see Alpha Centauri. For obvious reasons, it would be 180 degrees displaced. But down here in Orion would look the same, except Sirius, also being a fairly nearby star, it's only 8 light years from the sun, and actually therefore changes its position as viewed from Proxima B to be almost in the same direction as Betelgeuse, so a pair of really bright stars close together. So what if we decided to go there for a holiday? How long would it take? 24.2 light years, can't be too difficult. Well, a light year, light travels 300,000 kilometers per second for 1 year. You can work out that a year is all of this, 31 million seconds roughly. And so you can work out that a light year is all of this number, which I'm going to call 10 trillion kilometers, because it's nearly that. And so I have to thank Brian Lister for this next idea. If you set off when Stonehenge was being built using your Stone Age rocket, how far do you think you would have got traveling at the fastest speed that a rocket can go? Well, you'd have had 8,600 years to do it. And if you work out how far you've got traveling at 1,200 kilometers per hour, which is quite a reasonably fast speed. I think this is actually for a fighter jet, this sort of speed here, rather than a rocket. Then it turns out you'd have made it 1/100th of a light year. So I'm afraid you basically have got nowhere by comparison to the distance. You've went on 1/400th of the distance in 8,600 years, traveling at twice the speed of sound, I think that is. And so just to wrap up, we should talk a little bit about these gentlemen. We have here Yuri Miller, Russian billionaire, who put $100 million on the table to found the Breakthrough Initiative, backed by the late Stephen Hawking and sadly also Friedman Dyson here. They're both now sadly passed away. And to try and answer the big question, are we alone? And what they proposed was a mission to Alpha Centauri and the nearest stars. And they want to launch a rocket that will travel, or a spacecraft that will travel at 20% the speed of light. That's 140 million miles an hour. And the only way you can do that is to use a rocket to launch your spacecraft off the Earth and then deploy a star sail, a light sail, like this and fire a laser beam at it from the Earth. And the pressure of the laser light bouncing off the reflective light sail will accelerate the spacecraft continuously. And the advantage of this is you don't have to take your fuel with you. You can leave the fuel to power the laser on the ground. I think 99% of the weight of a rocket going to orbit is fuel, and 99.9% of a rocket going to the moon has to be fuel. So it's hopelessly inefficient. Whereas here we can leave all that fuel on the ground. So the idea will be a little spacecraft like this with a light sail, some photovoltaic panels to power the spacecraft, again powered by the laser, and a little transmitter which will try to use amplification from the big light sail to give it a nice big dish to transmit the signals back to Earth. And a huge array with a gigawatt of laser pointing up into the sky, continuously firing to power this thing during the acceleration phase, which will last for many months to get it up to speed. So I think with a 4-meter solar sail, they reckon that you can do this, accelerate to 20% the speed of light, and therefore make it to Proxima in 20 years, which is a plausible length of time for a space mission. They often take 10, 20, 30 years to reach their destinations. So this would be the spacecraft, the Breakthrough Star chip. It's a little computer with sensors and cameras using mobile phone technology and storage, and gets the power from the, as I say, from the laser using photovoltaic cells. So very, very lightweight it has to be. We're going to try and use not very much power to accelerate it, so it needs to be as light as possible, and it really would be that size, plus the 4-meter solar sail. And the idea would be to launch 1,000 of these in one go in a single spacecraft launch, and then fly this swarm out all towards Alpha Centauri in the hope that some of them get through without colliding with anything on the way, because a collision, even with a small speck of space dust, when you're traveling at 20% the speed of light, is going to destroy your spacecraft instantaneously. The other part of the Breakthrough project that is running already is Breakthrough Listen. And they're using the Parkes dish, made famous because it brought the TV signals from Apollo 11 back and relayed them to NASA, as in the film The Dish, which if you haven't seen is a great film. And this has been listening to 1 million stars across a very, very wide range of frequencies, a much better project in terms of listening to the universe than anything else. And the hot news is that in December 2020, they announced a detection from April and May in 2019 of what's called BLC-1, the Breakthrough Listen Signal number 1. And the BLC-1 radio signal is not coming from the Earth. They know that because they can point the Parkes dish at it and hear it, and then move it slightly off axis, and the signal disappears, only reappearing if you nod the telescope back to the original source. So it's not locally generated radio interference. They do have previous at the Parkes dish for announcing signals that turned out to be their own microwave oven cooking the jacket potatoes. So they are very careful about that these days. I kid you not. It's a very strange and unnatural looking signal. It's at 982.002 megahertz. Very narrow band, very narrow range of frequencies. Most natural radio sources are quite wide band, broadened out because the object that's giving out the radiation usually has a range of temperatures associated with it, and that range of temperatures gives a range of Doppler shifts to the signal. But artificial signals are made to concentrate the energy right tight in one band, so they're as easy as possible to receive and distinguish from all the background noise. It's got a rising pitch. That frequency is changing over time, and that suggests that what the object was accelerating towards us, whatever it was, giving it a positive blue shift, a Doppler shift to higher pitch. Now, they've studied the signal and they can't find anything other than the carrier wave. There's no modulation of any form that we can find, and no message hiding inside it. So if it's artificial, then it's a very strange artificial signal. It's the form you might have for a beacon or a dial tone for the galactic internet for you to connect, but it's got no data on it. And it only lasted 3 hours and then it stopped, and we haven't seen it since. So that's very, very intriguing indeed, and is actually by far the best candidate for a technological signal. And as I say, just discovered last year. So quite intriguing, but sadly it's gone away.
Oh,
So,
it counts under my hearing aid.
yeah, 982 megahertz is right in the mobile phone band for some countries, not Australia, but where the Parkes dish is. So we're just going to hope they didn't have some Japanese visitors. But we'll see. Maybe they came for a visit lasting 3 hours. That would be about right for a guided tour, wouldn't it? Who knows? And finally, I've just got one slide about Beta Centauri, the other star that we mentioned right in the constellation there, not to be confused with Alpha Centauri B. So the main claim to fame of Beta Centauri is it's not Alpha Centauri B. But it's quite a wacky system in its own right. It's a triple star system. It's got 3 big, hot, massive blue, bluey white B-type stars. 12, 11 and 4 solar masses, and they're 390 light years away, so they're not actually nearby. They're bright because they're powerful rather than because they're close. So I just thought I'd give that a mention because it never gets talked about. Poor old Beta Centauri. I don't know, Alpha gets all the fuss, but there it is. So thank you very much for listening. I hope you've enjoyed that, and I'll call that to a halt.